Okay, so moving on to section 3.2, how do we actually measure the rates of these reactions? You guys will be doing that in one of your first labs. It's the same as like if you were in a car and I wanted to measure the rate at which you are moving. It's the distance over time, right? So instead we're going to measure the concentration over time, which should change. So there's two things we could find regarding rate. You could find the average rate. Okay, so if you do your beginning and your ending speed over the time that you were moving, that will tell you your average rate, or you can find your instantaneous rate. Okay, so average rate is essentially just the change in concentration over the change in time. Okay, whereas the instantaneous rate is really found using calculus, right? Found with calculus. Has to do with, it's the tangent line at a specific instance, right? You look at tangent lines. Now, I'm not going to make you guys do the calculus, but you should be able to draw a tangent line to tell me what the instantaneous rate would be. Okay, another important thing to note is that reaction rates are stoichiometric. And what that means is you have to have the balanced equation and they are actually related to each other. So if I'm looking at this reaction, actually the rate of appearance of B actually matches the rate of disappearance of A. And what that means is this reaction is just a 1-to-1 ratio, A turning into B. So if I were to write what the rate is, I would write that the change in A, concentration of A, over the change in time. Okay, and it's actually disappearing, so that's why I'm making it negative. So that must have been my reactant. And it's actually the same as the appearance of B. So B is going to be positive change in concentration over change in time. And again, they are the same because this is a 1-to-1 ratio if I write out this reaction. Now, if it's not a 1-to-1 ratio, the rates aren't going to be exactly the same. For example, if it was a 1-to-2 ratio, then we would see maybe the products appearing at double the rate that the reactants are disappearing. Okay, so in this specific instance, these rates are equal, again, because they have the same coefficient. They're a 1-to-1 ratio. So I could write that the rate is equal to negative concentration of A over the change in concentration or change in time, which is also equal to the positive change in concentration of B over change in time. Okay, and what I want you to notice is I've actually written a generic rate formula, like to calculate rates based on the stoichiometry right here. So this is kind of how it works for a generic reaction, meaning generic reaction being coefficient of A times concentration of A plus little b. B makes C plus D and D. So the negative ones are the reactants, right? Reactants disappear. Positive ones are the products up here. And then I want you to notice the little a, little b, little c, and little d down here. These guys right here are the coefficients in the balanced reaction. So this will account for those changes in ratios, okay? So if they have a 1-to-2 ratio, that the rates will be, one will be halved or one will be doubled, depending on how you're looking at it. Okay, so we'll apply this in some different situations. So I'm looking at this example right here. Now notice these are all, this is a 1-to-1 to 1-to-1 ratio. Okay, now over time, so what I did in the lab is I did this reaction and I monitored the rate of disappearance of this reactant over time. So over time, the concentration went down, right? Which is what we would expect. And the rate, so I found the rate for each, what is that, 50 seconds. So after 50 seconds, so the change in concentration over 50 seconds is this. And I did it as time went on. So if you notice in this specific reaction, the rate is decreasing over time. It's going slower and slower and slower, which would make sense, right? Because I'm using up my reactant. So as I have less and less of it, my rate is going to slow down. So what is happening to the rate over time? It is slowing. As those reactants get used up, then it's going to slow down over time. So I graphed this right here. And when I was talking about tangent lines earlier, I have those drawn on here, the instantaneous rate. This would be my initial instantaneous rate, like I drew a tangent line right there. The rate at 600 seconds would be the tangent line drawn here. So you should be able to find the rate at a specific time based on tangent lines. Okay, Now, what would you expect the graph to look like if the ratio was not 1-to-1? So notice, remember up here, this is a 1-to-1 ratio. If I drew a graph, or I'm just going to sketch a graph here, for something that's not 1-to-1, I would be like, okay, well, if this one disappears, or sorry, appears at a certain rate, maybe this one is disappearing at a much faster rate. Okay, and you should be able to tell that that's faster because of this decrease, this in slope, or this very, very drastic change in slope, right? So a 1-to-1 ratio is not going to have the same slope. It's going to change, okay? This one is actually decreasing at a faster rate. Maybe twice as fast or 3 times as fast if we actually put numbers on there. Okay, so that's what the graph would kind of look like. So we're going to do some examples where we look at some data and figure out what's happening to the rate over time. So I'm going to do example 1, and then I'll probably have you try example 2 on your own. So example 1 says, consider the hypothetical decomposition of a compound A over time. So if it's a decomposition, that means I only have one reactant, A. So all I'm really worried about is what's happening to A over time. And notice I'm having less and less and less and less A, which makes sense because it is reacting. So it says calculate the average rate of disappearance over each of the 20-minute intervals. So if I want to know the rate of disappearance from here to here, rate, remember, is going to be the change in concentration over the change in time. So this specific one here is going to be 0.100 minus 0.067. That's molar over, that happened in 20 minutes. So that specific rate is 0.00165 molarity per minute. Okay, that's going to be the 0 to 20 seconds. Now you guys should try to calculate the 20 to 40, 40 to 60, and 60 to 80, and then check your answer. So pause it. Okay, this is what you should have gotten for your 20 to 40, 40 to 60, and 60 to 80. Now, as expected, the rate decreased over time because that reactant got used up. Okay, so B says, carefully plot the data on the graph and sketch the curve. Well, I already did that for you. I don't like sketching graphs by hand. I feel like I'm very, I don't know, estimation. So I like to do it online. I almost always use Excel. So I graphed it for you. It says determine the instantaneous rate at t equals 0 and t equals 30. So remember, instantaneous rate would be like whatever the tangent line is at this point, which is going to be difficult for me to draw on here, but I will try. Nope, yeah, that's not going to work. Okay, so you want to try to draw the tangent line right here. Yeah, that's definitely not a tangent. And then the tangent line at 30 seconds right here. Hey, that one was better. And then you could actually calculate based on that slope what the instantaneous rate is. And if you kind of guesstimate what that's looking at, I got about 0.002 molarity per minute here. And here I got about 0.0013 molarity per minute. And you can actually look at your numbers at the top and see if that falls into place. So if my instantaneous rate was 0.002 molarity per minute, well, that makes sense because the rate that I got over this time was 0.00165, so a little bit slower. And at 30 seconds, I got 0.0013 molarity per minute. Let's see, 30 seconds would be somewhere between 20 and 40. There I had 0.0011, so that would make sense. Okay, again, I'm not going to have you do the calculus here, but you should be able to draw a tangent line and then find the slope of that line. Okay, I recommend trying example number 2 and then checking your answer back. So I'm going to pause it really quick. Okay, so here's the work. I'm just going to kind of walk through it really quick. So I know that the change in N2O5 over change in time, so the rate of this one is negative 4.2 times 10 to the negative 7th. I said it was decomposing at this rate. It says, what is the rate of appearance of O2 and NO2? Well, remember, they're stoichiometric. So what I did is I actually wrote out this equation here that incorporates the coefficients, right? Negative this rate over 2 is the same rate of appearance of this, but it has a 4 coefficient from the balanced equation. So I put it here, equals the rate of appearance of oxygen, which just has a coefficient of 1. So once I have that set up, I actually plugged in the rate for N2O5 and multiplied it by 1/2 essentially, and then I could calculate the rate of NO2 and the rate for O2. Now, you guys might be able to look at this number and be like, I can figure that out. This is a 2 to 4 ratio. So I know this is going to appear twice as fast as this one is disappearing. Oh, look at that. 4.2 times 10 to the negative 7th doubled is 8.4 times 10 to the negative 7th. I also know if this is going at a rate of 4.2 times 10 to the negative 7th, oxygen is going to appear half as fast because it's a 2-to-1 ratio. So look at that, 2.1 times 10 to the negative 7th is half as fast. Guys, you might be able to do that just by looking at the equation. That's totally okay.